We've worked out that for a mass of ideal gas particles inside a cube of side L, the pressure exerted by these particles in one direction is equal to the number of particles times the mass of one particle times the root mean square velocity of these particles squared divided by the volume of the box. In order to apply this equation to all three directions in the box, we need to account for the aspects of velocity and the distribution of particles hitting the other walls of the box. The average velocity of all particles is equal to all the average velocities of particles in each direction added together. But because there are a large number of particles in the box, we can assume that the average velocity of particles in the x direction is the same as the average velocity of the particles in the other two directions as well. All we really need to do is allocate the correct number of particles to each of the directions. In a box, there are three possible directions: up, down, left, right, forwards and backwards. So each particle in a box has a 1 in 3 chance of travelling in one of these three directions. This means that the pressure exerted by all of these particles in a box is spread amongst three different directions and gives us an equation for pressure of P equals the number of particles times the mass of one particle times the RMS value of speed of these particles, all divided by 3 times the volume of the box. To put it the same way as the ideal gas equation, we times everything through by volume. Pressure times volume equals the number of particles times the mass of one particle times the RMS value of the velocity squared divided by 3. In all of this discussion, we have alluded to what temperature is within this model of an ideal gas, but as yet, we haven't quantified it. We do that in the next podcast.